Energy is the ability to do work. When we have the ability to do work, we could transfer energy. When energy is transferred, it is called heat. Temperature is proportional to the average kinetic energy. Thermal energy is the total of all the kinetic and potential energy of all the particles in a substance. So if I have a room full of particles at 100 degrees Celsius and I have particles outside the room at -5 degrees Celsius, which area has greater thermal energy? The area with the greater thermal energy will be outside. Even though the temperature is lower outside, there are more particles. The total of all the particles will be greater than addition of all the total energy of the particles inside the room at 100 degrees Celsius. As temperature increases, thermal energy also increases. When things are at thermal equilibrium, they mean that temperatures are the same. There are in general 4 laws of thermodynamics. For this class, you are only responsible for 3 of them. Everyone knows the first law of thermodynamics. It is called the conservation of energy. Since energy is conserved, that means it cannot be created or destroyed. It only changes form. The second law of thermodynamics says that heat flows from hot to cold. It will never go in the opposite directions. So anything that is hot will always get colder, and once the cold substance or object receives that heat, it will get warmer. Entropy, which means chaos or randomness of an isolated system, always increase. Example, the universe is expanding. As the universe expands, there's a greater opportunity to increase the randomness, so entropy is increasing. The 0th law tells you things can be in thermal equilibrium. What it states, if 2 systems are in equilibrium with the 3rd system, then they are all in equilibrium to each other. Heat can be transferred 3 ways. The simplest way is by conduction. Conduction requires direct contact. That means the objects must touch each other for heat to transfer. It occurs because the molecules in the objects will collide with each other to transfer the energy. The second type, it is called convection. This is movement of matter, usually due to a difference in density. So there's a circulation of currents due to the difference of density. This is why in the wintertime we have warm winters in California, and in the summertime we have cool summers. The cold air in the wintertime is blown out to the ocean. The water warms up the cold air because water has a high heat capacity, able to release a lot of energy to heat up the cool air without changing its temperature. Once the cool air is heated up, it is blown back to land and the cycle repeats. In the summertime, the hot air is pushed out into the ocean. Since the ocean water has a high heat capacity, it absorbs the excess heat without changing the water temperature greatly. Because water has a high heat capacity, the cool air is then blown back into land and the cycle repeats. Conduction and convection needs a medium in order to transfer heat. Medium is another word for particles must be present. Radiation is a transfer of energy using electromagnetic waves. That is like radio waves, microwaves, light waves, X-rays. Radiation, unlike the other two, do not need a medium. Example of this is the sun heats the earth. Sunlight travels through space, in which there is In general, there is no particles in space. Heat capacity determines the rate in which things heat up or cool down. These three pretty much means the same thing except for one difference in each. Heat capacity is the heat needed to raise the temperature of an object 1 degree Celsius. Specific heat capacity is exactly the same thing. There's a change in 1 gram of substance. So it is the heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. Molar heat capacity is the heat needed to raise the temperature of 1 mole of a substance 1 degree Celsius. So they all change the temperature by 1 degree Celsius. Heat capacity is a generic statement requiring heat need to change the temperature by 1 degree. Specific heat capacity is the heat required to change 1 gram of substance 1 degree Celsius, and molar is to change 1 mole of a substance 1 degree Celsius. How does specific heat capacity work? If the value is low, the system heats up and cools down very quickly. So metals have low heat capacity. This is why we use pots and pans made up of metal to cook our food. Substances that have high heat capacity, example of that is water, will heat up and cool down very slowly. So for example, aluminum has a value of 0.900 joules per gram degree Celsius, while water's constant is 4.184 joules per gram degree Celsius. If I have 1 gram of aluminum and I want to increase it by 1 degree Celsius, I only need 0.9 joules of energy. If I want to decrease it by 1 degree Celsius, I only need to release 0.9 joules of energy. However, for water, the capacity is 4.184 joules per gram degrees Celsius. So if I want to increase it by 1 degree, I need 4.184 joules of energy to heat it up. And to cool it down, I need to remove 4.184 joules of energy. So calorimetry is measuring thermal energy change due to a physical or a chemical change. To measure the heat transfer, we use something called a calorimeter, so a device used to measure thermal energy. In high school, our calorimeters are made cheaply by styrofoam cup, but real scientists use something called a bomb calorimeter. Inside the bomb calorimeter, there's something called a bomb shell. The bomb shell contains the sample that needs to be tested. Surrounding the bomb shell is a known amount of water, a thermometer, and a stirrer. The sample in the bomb shell is heated. It releases heat to the surrounding water. The surrounding water's temperature will be recorded, and the stirrer is used to make sure that the water temperature remains constant. After the sample stops burning, the transfer of heat from the burnt sample to the water can be calculated using the water's information. Because the temperature is measured before and after the burning, and we know the constant for water. So the calculated heat transfer divided by the amount of sample burned will give you the energy produced by that sample. This is the heating curve of water. Every substance has a heating curve similar to water. Their melting, boiling, freezing points will differ. Width and the height might vary. However, in the vertical axes, every substance will have temperature and kinetic energy. In the horizontal, it will be heat, potential energy, or time. So for water, anything below 0 degrees Celsius is a solid state. So right here is all solid. Once we reach the freezing point, which is at 0 degrees Celsius, you will have both solid and liquid. At the start, it will be all solid. As we go towards the right, heat and potential energy is being added. The solid is turning slowly to liquid. Once we reach the end of the melting point, this will all be liquid. However, in between, we will have both solid and liquid. At 0 degrees Celsius liquid, temperature increases and we only have pure liquid. Once we reach the boiling point, at the beginning, it will be all liquid. As we begin to vaporize, more liquid will turn into gas. So here we'll have both liquid and gas. Once we reach the end of the vaporization process, we will only have gas. And then afterwards, it will all be gas. If you notice, during a phase change, there is no change in temperature. The temperature remains constant. At 0 degrees where the phase change is occurring, it is a flat line. So there's no change in temperature. Only thing changing is my heat energy or potential energy is increasing. If I'm going to the right, it is decreasing if I'm going to the left. Same thing happens when it's vaporizing at the boiling point. It is flat. The temperature remains 100 degrees. So during a phase change, there's no change in temperature, but what is changing is potential energy. So potential energy or heat is increasing to break bonds or decreasing to make bonds stronger. In the heating curve, you could also locate the different types of phase changes. For water, at 0 degrees Celsius, as I go to the right, more heat energy, potential energy is being added. It is melting. Opposite of melting is freezing. These are phase changes. If you notice, there's no change in temperature. Only heat energy or potential energy is increasing or decreasing. At 100 degrees, there is also another phase change. A phase change, if you do not know, is going from one state of matter to another. So melting and freezing, it is either going from a solid to a liquid or liquid to solid. Vaporization is also another phase change. It is going from liquid to gas. Condensation is the opposite. It is going from gas to liquid. Again, during a phase change, the temperature remains at 100 degrees Celsius, but what is increasing for vaporizing is the potential energy or heat energy. For condensing, the heat energy and potential energy are decreasing. Solid to a gas, this is called subliming. Example of that is CO2. You see it in the solid state, CO2 ice, and gas. You do not see the liquid phase. Opposite of subliming is depositing. So we're going from gas to solid. It's called deposition. Example of deposition is if you have an old or a cube refrigerator, when you open the freezer to take something out and you close it, air particles get trapped. Temperature drops quickly, so the gas does not have time to liquefy, so it becomes a solid and it makes a deposit on your freezer walls. So every so often you have to defrost your freezer or you have a layer of ice accumulating. In order to have a better grasp of this chapter, it is wise to know some of the definitions. The definition of boiling point is vapor pressure of a liquid equals the atmospheric pressure. Our atmosphere has particles in the gas phase. When it is in the gas state, gases will exert pressure. That pressure from the gas is called atmospheric pressure. When boiling point occurs, a substance that is in the liquid state will start changing into a gas. That gas is also known as a vapor. Since it's in the gas state, it will exert something called a vapor pressure. When the vapor pressure equals the atmospheric pressure, boiling point will occur. This is why when you climb up a mountain, there's less particles in the air. So atmospheric pressure is lower. So the boiling point will occur at a lower temperature. Vaporization is a phase change. An object is going from a liquid to a gas, and it occurs at boiling point. So that means when the vapor pressure of the liquid equals the atmospheric pressure. Evaporation is also a phase change in which a liquid goes to a gas, but it occurs below the boiling point. Dynamic equilibrium is when the rates of exchange are the same. Example of that is if we have a classroom of 35 students and outside the classroom there is 1,000 students. If 5 of the students in the class leave and 5 of the students outside the classroom enters, the exchange rate is the same. We have 5 leaving, 5 entering. And when that rate occurs at the same time, that is called dynamic equilibrium. There are 3 sets of dynamic equilibrium possible. The melting and freezing rate of exchange may be the same, vaporization and condensation, sublimation and deposition. Now that we know where the states of matter and where the phase change occurs, we could also calculate how much energy an object gives off or absorb. In order to do that, these are the following equations we must use. Any single time there is a temperature change, the equation becomes Q equals mc delta T. Delta T means there's a change in temperature. Whenever there is no change in temperature, we must use Q equals mHF at the melting and freezing point, and Q is equal to mHV at the boiling point. The other thing you need to note, at the beginning of the melting point or the end of the freezing point, we only have solid ice for water. This right here is 0 degrees ice. At the end of the melting point or the beginning of the freezing point, we have only water, and this is at 0 degrees Celsius water. Anywhere in between right here, we will have both solid and liquid. At the beginning of the vaporization point or the end of the condensation point, we will have 100 degrees Celsius water, just liquid. At the end of vaporization point or the beginning of the condensation point, we will have 100 degrees Celsius steam. But anywhere in between, we will have both liquid and gas. When we increase the temperature, we are going to the right, and that is called an endothermic process. Heat is being absorbed, and so it's a positive value. If I go in the opposite direction, this is called an exothermic reaction. Heat is being released, and it will be negative in sign. Remember, when we have an endothermic process, since the heat is being absorbed, the bonds are being broken. This is why a solid can become a liquid, and a liquid can become a gas. When an exothermic reaction is occurring, heat is being released. So the particles are losing energy, so the particles get closer and closer together, forming bonds. The equations that I just showed you on the heating curve are Q equals mc delta T. Whenever there is a temperature change, we will use Q equals mc delta T, in which Q is heat. SI unit is joules. In the imperial system, we use calories. M is mass in grams. C is the constant in joules, grams, degrees Celsius, or calories per gram, degrees Celsius. Delta T is temperature. Remember, triangle means the change in. It is temperature final minus temperature initial. It could be in degrees Celsius or Kelvin. When there is no temperature change, we use Q is equal to mHF or Q equals mHV. Q again means heat, and it can be in joules or calories. M is in mass, which is in grams. HF is called the latent heat of fusion, and HV is equal to the latent heat of vaporization. For every substance, there are 5 constants. You will not be required to memorize these constants. They will be given to you. If they are not given to you, you will need to solve. So for water, there is a heat capacity in the solid, liquid, and gas state. It also has a heat of fusion where it's melting and freezing, and it also has a heat of vaporization where it's vaporizing and condensing. In the next set of videos, we will be working through the 3 main types of calorimetry problems using these equations.